All right, today we're going to talk about dot products. So there's two representations of dot products. You can either have an algebraic representation, which is simply, if we look at the equation here, it's going to look like that you're multiplying the two vectors, but that's going to be the dot product. So we're going to multiply the x components and add it to multiplying the y components. The other representation is a geometric, in which case we get that the dot product is the magnitude of each vector multiplied together times the angle between them. So in general with that one, we're going to think more about the angle. How is the angle represented? So if you wanted to take that, the dot product equals the magnitude of v times the magnitude of w cosine of theta, and you wanted to solve for theta, we would divide by the magnitudes, right? So those would cancel. And whatever we do to the left, we'd have to do to the right. So we get cosine of theta equals the dot product divided by the magnitudes. And if you wanted to take it one step further, then you would do theta equals arc cosine, right, of that quantity. All right, so now let's actually get down to computing some of this, right? So I've given you two vectors. This first one's in I and j component form. So you've got u equals 3i minus 4j and v equals negative 2i plus 3j. So if we go ahead and look for the dot product u times v, then we're going to go ahead and I think that the algebraic approach is generally a little bit easier. So I'm going to do u times v equals the 2x component, which is 3, times negative 2, plus the 2y component, so the j component's negative 4 times 3. So we get negative 6 plus a negative 12 equals negative 18 is the dot product there. Okay, on this next one, it gives it to you in component form. So if we're looking for the dot product, same idea. We're going to take the two first components of the x components, 2 times 5, plus the two y components, 2 times 5, 6 times 5 plus 2 times 5. So we're going to get 30 plus 10. So we get that quantity is 40. Okay. On this next one, we're going to look at what it means to be an orthogonal projection. Orthogonal means that it's like a right angle or 90 degrees, and then the projection means that literally we're projecting or putting it onto. So in this case, we're going to look at the projection of v onto w. So notice they start off with that blue vector v, and if they project it onto w, they're kind of bringing it down to w in this case, but it is at, if you look at that right angle, right? Okay, so let's just think about what we know. And that last triangle is super helpful for us, right? It gives us that right angle. So if you wanted to think about, we have in this triangle, if this is our theta, we've got the hypotenuse, which is vector v, the magnitude of vector v, and we've got our adjacent side is that p. So in this case, we have cosine. Cosine of theta would equal the magnitude of p divided by the magnitude of v. So solve for p in this case, because that's what we're looking for. So we multiply both sides by this magnitude of v. And you get that the magnitude of p equals v times cosine of theta. And if you look at what we just did above, I can now replace, so I've got magnitude of v still, but replace cosine of theta with v times w over the magnitude of v times the magnitude of w. That's what we just did above, right? So here we get that p, the magnitude of p, is equal to the dot product, right, v times w, all over the magnitude of w. But if I actually wanted to have the vector p, that's a scalar right now, right? That's the length of that vector. But to actually get vector p, I'm going to take the length of it, which is that dot product, over the magnitude of w, and I'm going to multiply it by the direction of w. So in that case, you'd think about just multiplying by the vector w, and that would give you a vector. But I don't want to change the length, so that's why I divide it by the square root of that the magnitude of that vector. So this is multiplying by the unit vector w. So this is multiplying by the unit vector w. This is the length, right, of p unit vector w to give you the direction, which therefore implies the projection of v onto w, and that's the notation we usually use, equals, I'm going to leave v times w together because that's the dot product, and that's actually probably easier to do than like v times w squared, all over the magnitude of w squared times the vector w. Okay, so let's go ahead and do some of this mathematics. So if we want just the dot product of u times w, we're going to do, sorry, that should have been v times w. We're going to do -2 times -3 plus 5 times -7. So we get 6 plus -35 equals -29. Okay, the next thing, if we're trying to find this projection, we're going to take that dot product, which is -29, divided by, we now need the magnitude of w. So we're going to do the square root of -3 squared plus -7 squared. So we get the square root of 9 plus 49. We get the square root of 58. So this is going to be -29 all over the square root of 58. Then we're squaring that times the vector w, -3, -7. So here we get -29 all over positive 58 times -3, -7. This out front, if I simplify it, may be easier to do first, is -1/2 times -3, -7. So then when you multiply it through, you get a positive 3/2 and a positive 7/2. So remember that gives you a vector, right, both length and direction. Okay, looking at this next part, we now want the angle. So remember that cosine of theta equals the dot product, which in this case is -29 all over the magnitude of v, and we don't know the magnitude of v yet, so let's look at that. Magnitude of v is equal to the square root of -2 squared plus 5 squared, square root of 4 plus 25, square root of 29. So the square root of 29 times the magnitude of w we got up above is 58. So then we get -29 all over the square root of 29 times 58. I'm actually going to divide into 29 times 2. Because then I think you'll recognize, oh, hey, I can pull out a 29. -29 over 29, square roots of 2. The 29's cancel, I'm left with -1 over the square root of 2. In this case, to actually talk about what that angle is, though, you probably recognize -1 over the square root of 2 is 45 degrees. But the question is, okay, in this case, if it's negative, is that -45 degrees? Is that, in the second quadrant, is it 135 degrees? So I would just maybe think about what these would look like graphically for a second. Like, hey, if I went -2 up 5, this is the first factor, and then we join them using the same initial point in this case, and then I go left 3, down 7. In this case, if you just think about this angle between them, it's got to be bigger than 90. So in this case, it is going to be an angle of 135 degrees. Okay. This next part, the reason why I put a little picture over here, this is not the same example, but let's just think about it in this example. So if you have Q is going to be the entire length when we are trying to project V onto P, right? Q is this length between them. So therefore, if I wanted to represent Q, think about it as being Q, maybe I'll write it this way. Vector, P is my projection, so P, the projection, plus Q should equal vector V, right? You'll notice that's just adding the two vectors. You got tip to tail there, and we'd end up with V. In this case, then, if I wanted to solve for Q, I'm going to take Q equals V minus the projection. So that's what we're doing here. Okay, so my vector V is -2, 5, and my projection is 3/2, 7/2. So remember here we take the first components, -2 minus 3/2, and then we do 5 minus 7/2. To make my life a little easier, I'm going to make it a common denominator, so this is really 10/2, and this is really -4/2. So when I do -4 minus 3, I get a -7, and they have the same denominator of 2. And then 10 minus 7 is 3/2. You should notice there's a little relationship there, right? Okay, so finally, if these really are orthogonal, when I multiply vector W times P, whenever things are orthogonal, so they're at a right angle, you should get that they equal 0. So we're going to have 3/2, 7/2. Oh, sorry, my bad, wrong one. So vector Q is -7/2, 3/2. And we're doing the dot product with that and W, which is -3, -7. So we're going to do 7/2 times -3 plus 3/2 times -7. So we get a positive 21/2 minus a 21/2, and we do get 0. All right, we're all done with that problem. I've got one more practice of this, just because I think this process is a little tricky sometimes. So let's take a look again. So the dot product of these two. So we're going to take -2. The problem is this is really like 0 I plus 4j. So there's actually no I component there. So we're going to have times 0 plus 2 times 4. So we do get an answer of 8 here. Okay, projection of V onto W. We're going to take that dot product, which is 8, and divide it by the magnitude of W, which is simply 4 squared, which is 4. So divided by 4 squared times our vector W, which is just 4j. So we'd have 8 all over 16 times 4j. These would cancel. We'd be left with 2j. Okay, so that's the projection of V onto W. If we wanted the angle between them, right, now we do the cosine of theta equals the dot product, which is 8, all over. Now we also need V. So the magnitude of vector V is -2 squared plus 2 squared, which is equal to the square root of 8, which is 2 square roots of 2 if you wanted to break that down, right? 4 and 2, 2 and 2, there's one set of pairs and one left over. So we'd have 2 square roots of 2 times 4, which is the magnitude of W. So we'd have 8 all over 8 square roots of 2. So we'd have 1 over the square root of 2. In this case, once again, like if it helps you, I would just think for a minute, okay, -2 is left 2, up 2, so we're talking about this vector, and then when we join that with y, which is a positive 4, notice that angle is going to be smaller than 90, so we do just get 45 degrees. Okay, so now as we take V, vector V, which is -2i plus 2j, and we subtract our projection, which is 2j, we are left with just -2i. So then doing the dot product, in this case I maybe would think for just a minute, like this is -2i plus 0j, just to make sure we don't forget about that, times W is 0i plus 4j, right? So dot product, we're going to multiply those two first components, -2 times 0, then 2 seconds, 0 times 4. So we get 0 plus 0, so we do get 0, which is what we want, and meant that it was 90-degree angle. Okay, this last one, we're going to look at force. And it says, work done as a dot product. Suppose F is a constant force applied to an object along the vector PQ. The work is done as given. So we're simply going to plug some things in here. So in this case, our force, it says a force of 1,200 pounds is required to tow a trailer. Find the work done towing a trailer 310 feet along a flat stretch of road. Assume the force is applied in the direction of motion. So here, our force is going to equal that vector, which is going to be 1,200 times cosine of how far the angle is moving. So in this case, cosine, if you think about this trailer, right? We got this trailer, and it's being pulled. It's going to be pulled kind of this way, so that does not have an angle at all, right? The direction it's moving and the force is moving the same, so it's going to be an angle of 0. Sine of 0 will be that force vector, right? You can think about it literally as 1,200 times 1, 0. So that force vector is going to be 1,200, 0. Okay, PQ, if you want to think about PQ, that vector is going to be the 310, right? That's the work you need to do. And we're going to move it just to the right, but we're not moving up and down at all. So we've got 310, 0. I guess I'd say the force why I wrote it in terms of sine and cosine is because you'll want to, sometimes there will be an angle, right? I'll maybe pulling up slightly. Okay, so therefore, the work done is the dot product of these two, 1,200, 0 times 310, 0. So we'd have 1,200 times 310 plus 0 times 0, which is 372. And our label here is actually foot-pounds. If you wanted to double check that, right, you could have done the magnitude of that force vector, right, would have been 1,200. So if you want to check the other part of the formula, you could do 1,200 because the magnitude of the force would equal 1,200 because you'd have 1,200 squared plus 0 squared root is going to give you 1,200. The magnitude of PQ, right, that vector PQ, is going to be 310. Similar reasoning. 310 squared plus 0 squared root is 310. And then cosine of theta, which in our case theta is 0. So we'd got the same answer. This is 1 times those two together is at 372,000. Okay, there's one example in your homework as well that has an angle in there. Same process, just plug in the angle. And there's a video that goes along in the homework if you need any help. Good luck.